This week's topic is interpreting geologic history through relative dating, which is to say we're going to learn how to read rocks. We're going to be talking a little bit this week about James Hutton, who is called the father of geology, and his famous quote is that the present is the key to the past. He stated that if you look at the rate of how the Earth is changing now, then that can help us get a clue as to how old the Earth might be. And he was one of the first people who proposed that the Earth was very old. In his lifetime, like many of the other scientists we've studied, he was not taken seriously until his student, Charles Lyell, who was much better at explaining James Hutton's ideas, came along and wrote a book called The Principles of Geology. And that was one of the books that inspired Charles Darwin, who eventually wrote the theory of evolution through natural selection. So we're going to learn the 5 principles that Charles Lyell and James Hutton laid out to be able to read rock. The first is called the principle of superposition. It states that when sediments are deposited at the bottom of a lake or ocean, they pile up in layers. In these horizontal layers, the oldest rocks are on the bottom, and the youngest ones are going to be at the top. The second principle is the principle of original horizontality, and it states that sediments are always deposited in flat horizontal layers. So if you see rock layers that are slanted or folded, they had to have been changed after they formed. And you can see here that layers are first horizontal, and so if you see layers that are folded, that must have happened after the rock formed. The third principle is called the principle of cross-cutting relationships. It states that if rock layers are interrupted by a fault or unconformity, the interruption is younger. You can see here that pressure can cause rock layers to fault or break in half like this. And we know that because the fault cuts through the layers, the fault happened after the rock formed. The other type of interruption we can have is called an unconformity, and that's when a part of the rock's layers are erased by weathering and erosion. And so this would commonly be seen if you have a bunch of rock layers that are going in one direction, and then there seems to be a significant break and all the rock layers suddenly change directions. That's because part of the rocks have been eroded away, and then new rocks piled up on the new surface. The fourth principle is the principle of igneous intrusions. It states that if magma intrudes or melts through rock layers, the igneous rock that forms when the magma cools is younger than the rock layers. And so you can see here that magma can come up from deeper inside the earth and cut through an existing rock. In this example, we have the metamorphic rock gneiss, and then this vein of basalt that is dividing it in half, and clearly the gneiss had to have happened first and the basalt intruded in later. And the last principle is called the principle of inclusions, and it states that if one rock is included in another rock, the included rock is older. So in this example on the right we have rock A, and in rock B we see parts of rock A are included in it, so therefore rock A would be older. The goal this week is to be able to use these 5 principles to put rock layer diagrams into a sequence from oldest to youngest. We'll practice this skill in class, but here's an example of how we can unlock the secret to reading rocks. So when I look at a rock outcrop like this, I'm going to attempt to tell you how I would tell the story of this. And we know from the principle of original horizontality that water deposited the sediment and it formed horizontal layers of sedimentary rock that might have looked like this. And you can see the water on the top. Second, tectonic pressure caused the layers to fold, and additional pressure might have caused them to rip apart and fault. As this rock was exposed to weathering, it would have become flatter, so weathering and erosion levels the landscape. Water deposits the sediment on top, and it forms more horizontal layers of sedimentary rock. And then we see here that the magma from deeper inside the earth intrudes the rock, and we know this happened towards the end because it goes through all the layers. And the magma cools slowly, forming an intrusive igneous rock. So basically on the left we have a picture that I got off the internet, and on the right is my recreation of that picture step by step. This diagram here is a cross-section of parts of New York State. You can see that if you were a person walking from left to right, the type of bedrock that you'd be walking over would change, and walking from left to right, you'd be walking from the older bedrock toward the newer bedrock, and you wouldn't see any kind of tilting, but you would be, if you look at this cross-section, you can see that all these layers started off horizontal and then were tilted upright. Here we have another map of New York State, and you can see that there are these layers of bedrock that go from east to west, and the reason that they change is because of the same thing we were just looking at. Different types of sediments and rock formations were laid down and eroded, and so the ages of these rocks changes as you go throughout the state. And here's how it looks in your reference table. Notice down here in the lower left, the type of symbol tells the age of the bedrock in each part of New York State. A fossil is the remains of a once living thing, such as a bone, shell, or imprint. Fossils only form in sedimentary rocks with a few exceptions, and the exceptions are pretty much volcanic ash. So, how do fossils form? Well, first rock layers are deposited from the bottom up. We see here that we have a fish in the water. The fish dies and sediment is covered over it. The bones of that fish may be preserved in that sediment either as an imprint or they're actually changing into rock. Then above that, maybe a dinosaur might have died and its bones are preserved. Above that we have a primate. And then so a person looking for fossils would find that the deeper that they dig, the further back in time that they would see. And if it meets two criteria, it is especially useful for relative dating, and it's known as an index fossil. And those criteria are, it has to be a species that's found over a wide region, which means that it's an animal or a plant that was everywhere. And second, it has to be a species that's only on Earth for a short period of time. So why are these useful? Well, let's pretend you're digging up a treasure chest. Let's say you open the treasure chest and you find some silly bands, a bunch of Michael Jackson CDs, and a basketball. So which object would be most useful in telling you how old the chest is? Well, the answer is the silly bands, because these are something that was only popular for a short time, whereas the Michael Jackson CDs or a basketball are timeless objects that people have had for many, many decades. Well, the index fossils are found on page 8 and 9 of your reference table, and you can see down here at the bottom there's all these lettered animals and plants and their fossils. And then, if you look in this section here, it shows the time distribution of fossils. And so it would have a category of creatures, such as dinosaurs, and then it would have one type of dinosaur. So you'll see in the dinosaurs bar, it would have letter L, which is Silophysis. And dinosaurs existed for that entire bar, but that one animal only existed for a short time. So if you find that one animal, that tells you that you're towards the late Triassic, and that helps you date other objects and animals and fossils that you find in that same layer of rock.